So coming to the next module, latch versus flip-flop is the first portion we'll be dealing with. So this module actually deals with sequential circuits. So in module 3 we have dealt with combination circuits, and in module 4 we will be dealing with sequential circuits. So in sequential circuits, the first portion we will be dealing with is latch versus flip-flop. So latch or the flip-flop is the basic building block of a sequential circuit. Okay, so sequential circuit is a module name. So in order to study about sequential circuits, we should know about the basic building blocks of sequential circuit, which is the flip-flop. So when we talk about the flip-flop, first we have to go for the very basic circuit, which is the latch. Now the basic latch is formed using either an AND gate or a NOR gate, and it is something like this. So here you have two inputs. Here also we have two inputs. We are shorting that. We need only one input. So the connection is here. There is no connection here. Okay, so the connection is only at these points. So though it is crossing over, here we don't have a connection. So this is a basic latch. So like the circuit, from the circuit you can understand that there is no particular input to the circuit. Okay, so we don't have a input provision for this particular circuit. So what we are doing is we are just switching on the circuit. Every NAND gate, NOR gate, all the logic gates will have a VCC and a ground. So VCC will be 5 volt for digital circuits. Ground will be around 0.2 volt. So when you switch on the circuit, why do we need this VCC and ground? Because you have transistors inside the logic gates, and in order to turn on the transistors we need the voltage. So for that you have voltage 5 volt. So we are just switching on the circuit, that is we are making the IC or the logic gate active by giving the voltage. And when it is switched on, what happens is, suppose this Q, this point, this particular NAND gate, this NAND gate is 1 and this NAND gate is say 2. So the output of the first NAND gate becomes say equal to 1. There is no compulsion that it should be 1, it can be 0 also. I am just assuming that this is 1. Okay, so when it is switched on, when the power is switched on, the output of the first NAND gate comes to some voltage, which is either 0 or a 1. So I am assuming here that it's a 1. So what happens? This one is connected directly here to the input of the second NAND gate. So what happens is that one comes here, and when you give a 1 to both the inputs of the NAND gate, you get a 0 here. So what happens is this 0 is directly applied to the input of the first NAND gate. So naturally when you have a 0 at the input, the output will be 1 for a NAND gate. So what is happening here? When you are switching on the circuit, the output comes to some voltage, 0 or 1, and that in turn locks the circuit so that this input will remain at 1 and this output will remain at 1 and this output will remain at 0. Yes. So suppose while switching on the circuit, the initial voltage at Q was say 0. If so, here it would be 0, here it will be 1, that 1 will come here, so it will be 0. So when you are switching on the circuit, whatever output comes at the output of the first NAND gate, the output of the second NAND gate will be the complement of the output of the first NAND gate. So if this is Q, this is Q bar. If this is 1, this should be 0. If this is 0, this should be 1. That is the property of a latch. Okay. So here we are not applying any input, but when you are switching it on, since these are both inverter circuits, why do you call it an inverter circuit? Because NAND gate, here it is acting as a NOT gate because both the inputs you have shorted. So when you this will act, you know how you construct a NOT using NAND. So this is acting as a NOT gate, this is acting as a NOT gate. You have two inverters, that is two NOT gates connected back to back. The output of the first is connected to the input of the second. Output of the second is connected to the input of the first. That is back to back inverters. So instead of NAND gate, you can use NOR gates also. Okay. So normally, but we will be using NAND itself. But if you use NOR or NOT, anyways, it will be the same only. So if you have two inverter circuits which is connected back to back, where you don't have an input, no input. Okay. So in inverters, connected back to back, that is output of the first is connected to the input of the second, output of the second is connected to the input of the first. Okay, so in this particular case it is called a latch. Why do you call it a latch? Because when you are switching it on, you don't know, you can't predict what the output of the first NAND or second NAND is. You can only say that it is complement of each other. If one is 1, other is 0. If this is 0, this is 1. That's the only thing you can say. This can be any value, 0 or 1. Okay, so you can't predict the output because you don't know the input. Okay, because we are not applying the input. It is just coming up. So when the output is 1 here, that goes here and you get 0 here, 0 comes here and you get the output. So this does not change. If this is the situation, we are in, this will not change because here it is 1, that 1 comes here, it is 0, 0 comes here, 1. So this will not change. So the state in which the inverter is, the latch is, will not change unless and until you switch off the circuit. If you switch off the circuit, then switch on, then this can change. Because this can go to 0 and this can come to 1. Or it can be the same also. You can't predict. So until and unless you switch off the circuit or give an input, give an external input, force an input, because you don't actually have a input provision. But then if by any ways you are forcing an input to one of these NAND gates, then you can change the output. Otherwise, this is locked to the state in which it is while switching on the circuit. And the state of a particular latch is the state of the Q, not the Q bar. Q bar is the complement of Q. So if this is the state in which this latch is, then you say that the latch is in state 1, because the output of the first NAND gate is taken as Q. So, and that is 1. So the state is equal to 1. If this was 0 and this was 1, this would be 1, this would be 0, then it is said to be in state 0. So what is actually in normal English, what is a latch? Latch is the what do you say, the latch which you have in a door. So what is the use of that door latch? It won't allow you to go outside, and it won't allow anyone to come inside the room once the latch is locked. So similarly, in this latch also, the output does not change. Output stays the same until and unless you switch off the circuit, you open the door, or give an external input, or you do some forced entrance. Otherwise, it is locked. That is a latch. Okay. Now, what is a flip-flop? The basic circuit of a flip-flop is a latch, but there is a difference between flip-flop and latch. So in order to understand the flip-flop, so here also I am drawing NAND gates. Okay, so in the case of latch, you didn't have any input. In the case of flip-flop, you will have inputs. Okay, so you have actually 4 NAND gates. Here these two are connected together. These are your inputs. Yes, this comes here, and this is back to back connected like in the earlier latch. And this is what you call as, we called it as Q and Q bar in the earlier case. Now you will call it as Qn plus 1 and Qn plus 1 bar. And the input you will call it as S and R. And this particular short, you will apply an input there also, which is called a clock. Now, why are you applying this clock? So, as I already mentioned, this module deals with sequential circuits. So, what is a sequential circuit is, I had mentioned during module 3 that in combination circuit, you give an input, you get an output based on the inputs given at this moment. You change the inputs, you'll automatically the outputs are also changed. In the case of sequential circuits, output depends on present inputs and past outputs. Sequential circuit output. Sequential circuit output depends on present inputs and past outputs. So we are mentioning two different times. One is present, one is past. So when you are talking about present and past, you should have a clock to time the the present and the past. Okay, you need a clock to tell you the time. How do you say that a particular time is present? How do you say that a particular time is past? And which past? At what time in the past? Okay, for all those things, you make use of this clock. Now, what is a clock? So, we'll come to the flip-flop. Before that, we need to know certain basic things. So, what is a clock? Now, clock is just pulses like this. This is 0, this is 0, 1, 0, 1. Okay, that is a clock. Clock is also written as CLK for easiness. CLOCK is the actual way, but CLK is also standard. So it is a series of pulses. It is normally taken in labs. We take it from a clock generator. You have a circuit called the clock generator. You have it in all the digital kits. And from there you can take a series of pulses which will go on till the time you require. Okay, so so you get the clock from the clock generator, and this is called the clock time or the time period of the clock. Okay, from a low to high to another low to high, or you can take from a high to low to another high to low. Okay, so one high and one low, that much is the time period, which you can notate as capital T. So clock is used to define this present and past. What is a clock? Clock is a series of pulses, square pulses. Pulse means what? It is 0 and 1. You have just two values, 0, 1. These are just the transitions. Okay. You have only two voltages, 0, 1, 0, 1, 0, 1. Okay. So that is the clock. Now there are many more things about the clock which we will be dealing with in the coming circuits. So as of now, we'll take it as clock. Now this particular circuit, suppose I am keeping clock equal to 0. Okay. So if clock is equal to 0, we know that these are NAND gates. So NAND gate, if one of the input is 0, then we know that irrespective of the other input, the output is 1. For an AND gate, if one of the inputs is 0, that is, if you apply a 0 here, here 0 is coming, here 0 is coming, your output will be 1. Whatever you apply at S and R. So input does not affect the output of these NAND gates. So that is not what you need, because in the latch you didn't have an input. So you are going to the flip-flop so that it will accept an input, and based on the input you'll get an output. So the purpose of applying the input is not served because you are applying a clock which is equal to 0. Because when clock is 0, you give S and R 0 or 1, no problem. The output will come only based on the clock. So this output does not depend on S and R, which is not required. So what you will do is, you will apply clock equal to 1. So only if clock is equal to 1 does your output of the NAND gates, first two NAND gates, depend on the S and R inputs. So though we said that clock is high and low, a series of pulses, here until and unless I tell otherwise, whenever I say I am applying a clock, I am saying that the clock is equal to 1. Okay. So applying a clock means I am applying a 1 at that particular point. So clock is equal to 1 is what I am doing. Okay. So I am applying a 1 there. Now what I am going to do is, I am going to find out a truth table for this particular circuit. So I'll just draw it a bit smaller so that I can accommodate the, so this was my so here you have a connection, here you have a connection, Qn plus 1, and this is Qn plus 1 bar. Okay. Right. So now what is Qn and what is Qn plus 1? Qn is the previous output. Qn plus 1 is the present output. Now in some text it is written as present and next. Either ways it's the same. At a particular time t, if we are considering an output, that is Qn, and at a particular time t plus 1, that is called Qn plus 1. So either it is previous and present, or it is present and next. Okay, so it is at two different times. One is in the past, another is in the present, or it's in the present and the future. So either ways it's the same, just the usage is different. Okay, so that is Qn and Qn plus 1. Now what we are going to find out is, and now the basic difference between Qn and Qn plus 1 is, Qn is the output at a particular time. Qn plus 1 is obtained when you apply the next clock. So if these are my two clocks, at this particular time if I get Qn, at this particular time I get Qn plus 1 output. So previous clock, what was the output? Present clock, what is the output? Or present clock, this is the output. Then what is the output when the next clock comes? Clock means clock equal to 1. So that is the difference between Qn and Qn plus 1. So we have 3 inputs. So we'll write all the combinations. It can be any of these. Yes. Now, for certain reason, I won't take the first one. I'll tell you why later on. I am taking the second case. That is Qn equal to 0, S equal to 0 and R equal to 1. So where do we get this Qn? Qn is at this point itself, only the clock timing is changing. I'm taking the second clock and the third clock, or the first clock and the second clock. First clock, if I'm calling the output as Qn, second clock I'll call it as Qn plus 1. Second clock, if I'm calling the output as Qn, the output at the third clock I'm calling it as Qn plus 1. Similarly, at that particular time, Qn bar and Qn plus 1 bar at this point. Okay, so in the second case, I'm not taking the first case, I'm taking the second case. So initially, that is, we are talking about the previous state. Initially, this was 0. I want to know what is the next state. This is Qn. I'm going to find out what is Qn plus 1. Okay, so Qn is 0. That is what I know. So if Qn is 0, naturally this should be 1. Okay, S is 0. That is given. R is 1. So S0, clock 1, this is 1. 1, 1, this is 0. So this was 1 previously. Okay, so this red is the previous state. Previously, it was 0, now and 1. Now I am applying, I'll take it to the another, it was 0 and 1. So now I am applying 0 and 1 to S and R. 0, 1 to S and R. Okay. So this is Qn previous. This is the present inputs. Black is present input. And I am keeping the clock also. The next clock I am applying. This is already there. At time, say at the second clock pulse, it was 0, 1 here. So before the third clock pulse comes in, I am applying 0 and 1 to S and R. Then the third clock pulse also comes in. So I want to know whether this Qn and Qn plus 1 are the same or different. So if this is 0 and 1, naturally here it will be 1, 1, 1, here it will be 0. So what are we going to find out? We are going to find out the output at the third clock pulse. At the output at the second clock pulse is what is given in the red. Why did we take it as 0 and 1? Because that is what is in the table. Qn is 0. Qn 0 means this is taken as 1, the complement. Now, after applying these inputs, these outputs are like this. Now comes the catch. Here it is 0. So for this particular NAND gate, that is for the NAND gate 4, one of the inputs is 0. So naturally my output will be 1. And this output, this black output, the present output, that goes to this particular place. So for NAND gate 3, it is 1, 1. So it will be 0. So what is happening? The output is same as the previous output. So it is 0 itself. I am writing only Qn plus 1. I am not writing Qn plus 1 bar. Okay. So that is 0, 0, 1. Now I am changing the inputs. I am keeping it as the previous is again 0. This is 1. I am changing the inputs to, say, I'll take the first case. Okay. 0, 0. So if it is 0, 0, both 1 and 2 will have one of the inputs as 0. So the output is 1 in these two cases. So when the output is 1 in these two cases, in the earlier case we had one of the outputs as 0. That is the input to 4 was 0. So we could easily say that the output is 1. But in this case, both these are 1. If for a NAND gate, you have two inputs, one is a 1, you can't say what is the output unless and until you know what is the next input. So if this is 0, this is 1. If this is 1, this is 0. So if with one of the inputs as 1, you cannot predict the output. So that is the similar case here. Okay. For 3 and 4, one of the inputs is 1. We can't say what the output is. So in such cases, where you cannot predict what the output is, what you'll do is, you'll take the previous state also. That is the one in red. So here the 0 comes, and here, so that's actually the previous one. And here the 1 comes. So now what happens? The previous output 0 came here. So 0, 1, the output is 1. 1, 0, the output is, 1, 1, the output is 0. So here again it is 0. Now again it is output is 0 itself. I am just changing S and R. S I am giving as 1 and R I am giving as 0. R 1 0, here it is 1. 1 1, here it is 0. So in these two cases, one of the outputs have a 0. So when you have one of the outputs as 0, that is in 3, in logic gate, in NAND gate 3, one of the input is 0. So you can say that the output, present output is 1. And now what happens is when Qn plus 1 becomes 1, that 1 will come here, not the previous 0. Because when this 0 comes up, the output of the logic gate 3 changes to 1. So you don't have this 0 anymore. So this 1 only will come here, and 1 1, this will change to 0. So here it is 1. Because Qn plus 1 is 1. Next case is, again output is 0. Inputs are both 1. Now here the problem is, input are both 1, clock is also 1. So 1 1, this is 0, 1 1, this is 0. So now what happens? Both 3 and 4 have one of the inputs as 0. So both the output will become 1. Both the output is 1 means the starting logic, that is, this is Qn plus 1 and this is Qn plus 1 bar, or Qn and Qn bar, that is violated. So if 1, here it is 1, this should be 0. If this is 0, this should be 1. In this particular case, that is violated. So what happens is, when S is 1 and R is 1, you will not take the output. It is invalid. Next case is when output is 1. Output is 1. This is 0. This is 0 and 0. So I am taking it as, this is the previous 1 0. Zero zero means this is 1 1. You don't know the output because both are 1. In such cases, what should you do? You should take the previous. So here the 1 comes here, the 0 comes here, 1 0 makes it 1 again, 1 1 makes it 0 again. So here it is 1. Likewise, output is 1 and 0, input is 0 and 1. This is 0, 1, 1, 1, 1, this is 0. When you have a 0 at one of the points, write the answer to that or the output to that gate first. That 1 will come here. 1, 1, this is 0. So this is 0. Next is this is 1, this is 0. So this is 1 and this is 0. Since this is 0, you can automatically write the output as 1. That new 1 comes here. 1, 1 is 0. So here it is 1. Last case, So 1 means 0, like in the earlier case, like in this case. So both are 0, so these both are 1, which is invalid state. So this is what we get after applying all the inputs. Now what we are going to do, this is the big truth table. Now we are going to formulate a small truth table. This is Qn plus 1. We are not considering Qn here. So from here, SR, two inputs. So it is 0, 0, 0, 1, 1, 0 or 1, 1. Yes. So SR 0, 0 means this and this. In that two cases, you can see that when S is 0, R is 0, here it is 0, here is 1. So what you do is, you will find a relation between Qn and Qn plus 1. So if S is 0, R is 0, if Qn is 0, Qn plus 1 is 0. If Qn is 1, Qn plus 1 is 1. So what is Qn plus 1? It is Qn itself. If it is 0, 1, SR 0, 1, it is this and this. So in both the cases, irrespective of the Qn, the output is 0. So output is 0. In the case of 1, 0, this and this, Qn 0, output is 1. Qn 1, Qn plus 1 is 1. So whatever be Qn, Qn plus 1 is 1. 1, 1, both are invalid states. You can write invalid or put a question mark. Both are the same. So this is the truth table of SR flip-flop. Why do you call it a SR flip-flop? It is set reset flip-flop. Why set reset flip-flop? Because if S is equal to 1, then the flip-flop is set to 1. This case. If R is equal to 1, that is reset is equal to 1, then flip-flop is reset to 0. So that is why you call it a set reset flip-flop. If you don't have a provision to give the input in an SR flip-flop, then it is called an SR latch. Okay. So that is a difference between a flip-flop and a latch. And how do you find the truth table of a SR flip-flop? Now you can also write the equation for Qn plus 1 by writing the K-map for Qn plus 1. So what will you have here? Qn SR. So 0, 0, 0, it is 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, it is don't care, 1, 0, 0, it is 1, 1, 1, 0, it is 1, 1, 1, 1, it is don't care. So it is like this and like this. So Qn plus 1 equal to S plus Qn into R dash. This is the characteristic equation. Truth table is also called the characteristic table. That's why you call this the characteristic equation. So characteristic equation means equation for Qn plus 1 in terms of Qn and the inputs. So that is SR flip-flop.